Well, good morning and welcome to our seminar in Statistics, Optimization and Applied Mathematics. This is my great pleasure to introduce our speaker of today, Professor Nguyen Dinh, from the International University in the National University of Vietnam. And he's a big expert in the subject of today in Farkas lemma, several papers on this subject. This is a crucial tool in optimization, so it's our great pleasure to have you here. He has been in Alicante and Elche several times. I remember, for example, in 2013 we signed an agreement, collaboration agreement with the universities. So we are close collaborators and enjoy the talk. So thank you.
Thank you, Paul, for the nice introduction. And, my talk is what we call general robust Farkas lemma with application to robust optimization. So actually the aim is we try to apply to some robust optimization problem of this form. This is a very general form. And this talk can be a continuation of my talk here. About 2 years ago, I think so. At that time, we start with some concrete formula, concrete problem, robust Farkas lemma, and now it's one more step to generalization to very general inequality of this type. And the function f here is the function from, it depends on, each f depends on the parameter u, and u we call the uncertainty. So the uncertainty member belong to this is the uncertainty set. So we actually, something like this, we try to make the minimum of this function fx, but the function f depends, it's not fixed, it is among the set of a lot of the fu, like it is perturbed a bit like this. And so among all these things, each of u, we have this one problem. So the robust one is the thing we call the worst one. That means we take the supremum of this function, and then we take the minimum of this, and this is called the robust one. And so that's the reason why it appears here, the supremum here. And here we consider this one, the reason why sub appear. And in this talk, actually we will establish some of the following results. The robust abstract duality, the robust composite inequality, that means the first one related to the robust Farkas lemma, which related to the general function fu. And the second one here is composite functional inequality, that's special class of this one with the composite function. And the third one is from this one, from the second lower concretized, then we consider very many concrete form of the composite function, and it will lead to a lot of the Farkas lemma with the robust Farkas lemma. Come back to the cover and develop. Actually, until now, the first two Farkas lemma, robust Farkas lemma, have not yet been found in the literature, and up to my knowledge. And when we apply to special solution, special case of functions, we recover all the three kinds of this. And it should be mentioned that these three kinds of Farkas lemma, robust Farkas lemma, appear in here and there in the papers, especially some papers of the group of co-author with Chakuma, including here the two Professor Lopez and Professor Diego Bena. They make lots of 20 papers about like this on this one. But the thing is that each of the paper consider one of the case, and they make a Farkas lemma applied to robust optimization problem. But each kind of Farkas lemma was formulated in different way. So they approach by the linear one and use the tune of linear to apply to the convex and use like this. And now the problem now is I want to make it in the unified case. I sorting from this one, Farkas lemma for the first, and then I get this one and special files in this concrete case, and I get back all this one. So this can be considered as the unified approach to robust Farkas lemma, and that is actually the name of the paper. We do it like this, and I have to say this is published in Syrup, but I'm very lucky because one of the professor here is a referee for this, and they very.
You are inventing this.
So it is accepted and published already. And so the last thing is the application. So we applied this result to the application of the last three things here to the correspondent optimization, robust optimization problem is already appear. So I just want to apply the two new kind of things here to the new robust optimization problem. Is the robust DC, and we come back to convex, and we get back for the robust DC problem is very new, and this one we cover and discover some new result on even in the class of the convex. So the outline is it's the same like I tell you, some notation, and then the robust abstracts. Here that means that the robust abstract Farkas lemma, and then with the composite Farkas, the robust Farkas lemma with the composite functional inequality, and the several kind of the robust. When we come back, we show that our approach is unifying many ways to approach to robust Farkas many times here. And then the last one is applied to the robust optimization. That is, and so I have about how many time? How much about time?
1 hour.
It's about 1 hour. Okay. Okay. So I just actually the result later, and it's a bit more techniques, and it looks complicated. So I just show you the idea, mainly the idea. So first of all, we apply to robust optimization problem. So we should we concern with the optimization problem with uncertain data, like this problem with depends on U, the set of uncertainty. And the robust approach is one of the approach in the theory of optimization, and we consider something like this, the worst case, like this. And then the robust optimization attracts the attention of many mathematicians starting from very long time ago. So, and it has many applications like to the real world problems like portfolio and risk management. It's in 11, 12. It's here 11 here. That's robust portfolio optimization management and robust portfolio here. And there's some inventory management, logistics, revenue management, queuing networks, stochastic system and game theory, machine learning and statistics, energy system, public good area is presented in the 13. 13 is a very nice review about the application of in many areas of robust optimization problem. However, even in the paper, the review paper 13, we pay attention to one sentence. They say robust nonlinear optimization remain much less widely studied to date than its earlier linear counterpart, especially when the problem is nonlinear in the uncertainty itself. That means FU here is nonlinear in U, and in the presence of non-convexity, that means this one, the function f here is non-convex, or it is non-convex on U. But in our paper, we don't care about the U. The U can be anything. It not necessarily convex, not necessary, but the function f is also a very general case. In some special case, we consider f can be represented in some form, and it may have we may consider the case when the data is convex or something like this. But in general, it is not any assumption, except the function f is proper, of course. If it is always plus infinity but always minus infinity, we don't consider, we exclude it. In the recent years, many results on the optimality condition or duality, strong duality for the class of the problems of robust optimization were established, and they use robust Farkas lemma. And we are working with the two professors here, Professor Lopez and Gobena, a lot about the Farkas lemma. So we think that's one of the ways to develop is to reach the robust system. Is it okay to see that we can establish some robust Farkas lemma, and then we can apply to the robust problem or not? So many the robust Farkas lemma, like for the linear, for the convex, was established in this one, and so this show that the papers, many papers here show that we can use the robust Farkas lemma is a effective tool to study the robust optimization problem. And so, as I told you before, in each of the paper they use a typical approach to typical type of Farkas lemma. And so that is not what they do. What we do is that we try to create a very general form of robust Farkas lemma that can, which can be derived many nodes one in the literature, and that is the aim of our work actually here. So a bit from the elementary, what is Farkas lemma? So actually we consider the implication like this: x belong to A imply gx less than 0, like this. And each of the, and then we call that is one proposition. And then if we can find something equivalent to this, then we call it a characterization. Each characterization of this implication together with the pair like this, we call a Farkas lemma. And a Farkas lemma, we can have a convex DC or something like this. If A is convex, she is here actually we often write down this is greater than 0. If G is convex and this is convex, then we call convex convex. If it is convex and this is DC, then we call convex DC Farkas lemma or something like this. If and so on, okay. And the robust Farkas lemma this is the Farkas lemma. This one and each characterization, a pair of this we call a robust Farkas lemma. And the robust Farkas lemma means that the set A here, this A here still depends on U. So X belong AU and U belong to some uncertainty set U. So that means that we consider A is the intersection of all U like this. So you can imagine that we have the situation like this. A belong to U, okay. X belong to A, but the set A is not fixed. Now it's perturbed. It's perturbed. So X belong to AU. But for the robust, mean we want the certainty. We don't want uncertainty. We want a certainty. That means sure. That means we want this to belong to for any U belong to U. Is that okay? And that means that we consider A is the union of the all of this one. So when A have this form, and then we have the Farkas lemma called the robust Farkas lemma. So in the application, we try to, of course, the general problem like this you also can apply, but my aim is try to make it more concretely. So we try to apply to some problem. Robust problem DC. So here the F is and H is convex. So this is the difference of two convex functions. That's the problem. And the constraints depends on U. And so this problem we call the robust DC problem, because that means robust DC with, but the constraint here is convex. H of U are all convex. And the convex DC also have another form. This is the cone constraint, but here we have some infinite constraint like this. And the robust convex, that means when H equals 0, then we come to the convex function problem. The convexes also have two forms, and here is the linear. So we have this linear, semi-infinite linear, something like this. So mainly we aim to apply to this thing in the application. This on the notation, we use all the notation in convex analysis. So it's like this. We say a set C is with star closed. C in X star. X star is the dual space of X with the equipped with always with the with star topology, and the set C in this is called with star closed regarding V. If you have the closure of this in the with star topology in the set with V equal to C in the set with V. So it's closed regarding. And with star closed convex regarding, that means if we take the closure and the convex rule of C intersection with V, then it's equal to this. So we use mainly here two things: closed convex, with star closed regarding, and with star closed convex regarding a set. All the other notion are the same in convex analysis, but this one is epi with the S here is strict. So instead of here is normal with less than or equal, so we have the strict inequality here, and that we call the strict epigraph. And F is convex, of course, epi of F is convex, something like this. The set of all the convex function defined on X, we convex and lower semi-continuous. Then we said we put it in the collection is called gamma of X. And if you have a cone, a non-empty convex cone in Z, then S plus is defined by the dual positive dual cone. And if you have the vector value map like this from X to Z from the dome of X, then epi we write down epi S. S is a cone, convex cone in Z. We call epi S if you have Z it's equal to xz, but z belongs to h of x plus s. So it's the same like epi in the normal case, in the scalar case. And h, the function h is called s epiclosed or s convex if the epi-s is closed or convex, respectively. And that is, we now come to we consider the function here, and we try to come in this kind of problem. So x, y are vector space, locally convex Hausdorff topological vector space. U is uncertainty. F is this kind of function here. And now we set P. Px is the supremum of Fu x with 0. And Q is Qx star equal infimum of this one. And now you look at this one. We consider the problem, this problem, but each u you have one problem. So we have the family of the problem, but the function f is perturbed like this. It's uncertainty. So the robust form is this. Is that okay? The robust form, we make the bad one, the worst one. We take the supremum, the biggest one, and then we take the infimum. So here, but this is the supremum of this, and so we call this is p. Is that okay? So the function p is there, appear here. P is this. And then with this one, the dual problem of the robust will be like this. And so you see the supremum of this is of minus, then it's equal to the minimum of, the infimum of. So we set Q is equal to the supremum, Qx is this, the infimum of this. And so you have Qx star is the minus supremum of this is minus, so it's here. So with the P like this, so you see, if you take the P star, if you take the P star, so P star is what? P star is the supremum, the conjugate, we take this one minus this one, is that okay? And so it's minus of this, and then we take the supremum, and then it's equal to the infimum, and that is actually infimum of this. So P star x star is the infimum of this problem. So that is, so actually you have the infimum of this problem is minus P star x star. Is that okay? And the supremum of this is equal to, minus Q of x star. Is that okay? And so when you have the duality, means you have minus of this equal to minus of this. And so the strong duality means you have here. But in this paper we mean the strong duality means the dual problem attend. And so here instead of the supremum you have here the minimum. So it's equal to is minus of the mean of f u star x star y star, something with u belong to u and y star belong to y star, like this. So the dual like this. So but this is for the later use. We will come back to this. So we see the main problem we consider is there. But now you see the epi, so f star will be fx like this. So f star will be from x star multiplied by y star. And you have this epi of f star is in 3 dimensions. It is on this. This multiplied by this multiplied by this. And now we want to have a set in this one, and we take the project of this one, but we delete this one. We project to the first and the third. And so you have this one. And we take the project of the epi here, and we take the union here, and we call it the set A. And this set plays an important role in the whole of this the research. So we have actually this paper based on 2 lemmas. From these 2 lemmas, then we have everything. The first lemma, very abstract, is that we define the function q is there, and we calculate q star is this, and then we have p star less than q star by conjugate and less than q, and fps of q is this. A is the set, our set here is the subset of fpq and the subset of fpp star, and then you have this inclusion. So all of these things are very abstract. But we have this without any condition. You have this with very general case without any condition. In the case you have the supremum of this at some point supremum by u, but some point x bar here, that is less than the infinitive, then you have this one. So you come back here, what is it? FPQ here equal to the closed convex hull of this set A, like this. And in this case, the following are equivalent. So in this case, you have FP of P star. P star, you remember, P star is the function, the value of the function, the robust problem or later. And FP P star equal to the closure of A. So these 2 basic lemma with very abstract, but it will to some concrete situation, it will give us many nice results. And the first one, the third section is about duality, robust abstract perturbation duality. It means that we want to mainly establish. You remember we have P, this one, and we want P greater than H. So if this one, and if you have something equivalent to this, then this pair is called the Farkas lemma. So we have pair. Here is for any H, gamma V. Gamma V is, we have H belong to gamma V of X. So it means that H is from gamma X, so that you have dome of H star is inside of V, and V is a set of this. So that is a family of set. But when we consider a set V in this one, we only consider the function H, so that the dome of this inside that set. We have some special reason when we come to the special case, and we will see what it is. And this is a Farkas lemma. And B1, so B1 is Farkas lemma, and the Farkas lemma hold for all this one, all V, all H. And then the theorem say, if dom P is this, and if dom P is non-empty, and then we have Farkas lemma equivalent to this one. This one like the qualification conditions. This is qualification condition here. P star and A here. So you see the relation in the last page, you see FP star equal to the closure convex hull of this. And now if you focus only on the set V multiplied by this, but the implication of this one on this are equal. That means the set A or the set this one, no, it's something like a close regarding the set. Yes, like this. This is a qualification condition under this one. This condition equivalent to the Farkas lemma. And this, the last thing, 3 of this equivalent together. It means that you see, if you choose a V like this, then for any V of this one, you have P x star equal to this one. So it means that the robust strong duality. So that with Lopez and Gobena, you see that we have the here, and now the new paper you have something here more. The strong robust duality equivalent to some set formula here. So if we combine together, then we have 4. The set of 4 equivalent conditions. Is that okay? And that is included in this one. But we only, because this paper we focus only on Farkas lemma. And so this one we maintain in some theorem, and then we drop. We just focus on the first 2. That means this is Farkas lemma, and this is the qualification condition. It's okay. So it's necessary and sufficient condition for Farkas lemma. That's only on this. And of course, when we take v equals 0, and then we have something like this. And you can understand why is this. You can understand here is it. If you call this problem is the value is alpha. Is that okay? The value of this problem is alpha. So what does it mean? This means that you have this one, that's supremum to u of fu of x 0 y here, if you choose it equal to 0, and then the supremum here is greater than 0 for any x. Is that okay? Sorry, greater than alpha, and it is here. Is that okay? So when you have the equivalent here, it means that you have this greater than alpha equivalent to something. And suppose that the problem here attain the minimum at some point x bar. Is that okay? So this alpha equal to p of x bar, something like this. And then of course this equivalent gives you necessary and sufficient condition for x bar become the solution of that problem. Is that okay? So he showed that mainly the Farkas lemma focus on, first of all, if you have Farkas lemma, you for the suitable class, then you will have right away the optimality and sufficient condition for the optimality of some point. And that is why we consider here this greater than. And what is it? This is greater than h. So what does it mean? Greater than h, that means you have something here minus h instead of this is a linear problem. This is linear perturbation. Is that okay? We consider linear, then we consider this is a linear perturbation of this problem. But instead of this, you make minus h of x, like this. If this is convex, then you have the DC. Is that okay? And in that case, this is greater than h of x. Is that okay? See, that's great. Minus is greater than 0, something like this. And it is here. It's actually like this. And so when we insert the h to the right hand side here, we try to include the class of problem with the DC. With the DC, it's convex minus 2 things. So the general case we always consider with h, but in special case it's like this. So that is the first one is the robust abstract perturbation duality we call 1. That means without any condition, but as here. So in this case, when you have P double star, you remember P star is this, and P double star is something different from this a bit with the first lemma you have here. This is less than this, and Q star is this. There's some relation here, but whenever you have the relation of P double star equal to the supremum of this, then you have Farkas lemma. You also have here, this is this is also here, the duality. You have Farkas lemma equivalent to strong duality, robust duality, and you have equivalent to the qualification condition. In this case, it becomes like this. A star A is with star close convex regarding to this. So it's in any in some sense, some extent, to some extent, this equality included the convex case. The convex, some assumption convex is implicit inside, and then with the convex, then you have A is, if it is close convex regarding to this one, and then you have this one. You will see when we come back to the functional inequality with all the data convex, then A have a special form, and we can apply this theorem. So, and now we come to the section 4. The next section we come to the composite functional inequality. That means we try to make the function f become something like this: f plus g plus supremum of k round h of u greater than h, like this. The problem is we try to consider this one. We try to apply to this problem. And in this case, so you see, if you make this, if you take a look at this problem, suppose that the infimum of the problem RDC is alpha. Is that okay? And then you see, if this is alpha, and then you have fx minus h of x greater than alpha. For any x, satisfy this. Is that okay? That means for any x such that you have x belong to C, h u of x minus s for any u belong to u. This, if you have all this x satisfy this one, then this value is greater than alpha. Is that okay? But this is equivalent to, if you call IC and I minus s of h of u of x, like this, and then you will see this thing, this is I here, equivalent to I prime. This equivalent to x plus this x plus f of x is greater than h of x plus alpha. So it's something like some other function h prime. Is that okay? Or you can there is okay like a x tilde or something like this. Is that okay? Just a function if f is convex. If h is convex, then you plus alpha. Here is also convex, so it's no problem. Is that okay? So you see, this is G. This is K round HU. Is that okay? And then there's a function f here, like this. But because here for any x, for any u belong to u, so you have to put here the supremum u. Is that okay? And so it actually you have G plus f plus supremum of this greater than this one, and it is of the form like this. Is that okay? So if alpha is the infimum of this problem, and then u is equivalent to this one. So if you have something equivalent to this, that means Farkas lemma for this kind of inequality, then you will get the optimality condition for this. But of course we also get the duality by some calculation, then we will have. So we try to make a special case. The function this is a supremum of fu. This This is the supremum of fu here. But in this case, the function fu become very special like this. And then, but the problem is that this is fu without the value, the variable y like a perturb, variable. And so many ways to insert the perturb. The first way is we perturb only here is k of h of u, and then we make a little perturbation here. The first way, we make perturbation here. The second way, we use a function here, the function f, and only one perturbation variable and appear here. And the second way, we x is here, and then we insert 3 perturbation variable, and one is here to the f, one to the f, one to the g, and one to the h. One to the f here, one to g here, one to there. And the last one, we have two perturbation, one x1 z, x1 to f, and z to this one. So it's excellent. We try the three way of perturbation. Input the perturbation variable like this. It gives us the set A here now become the three form, different form. With the 7, with the function defined by the 7 here, with the perturbation list, perturbation 8 and 9, 3 ways give us the set A become BCD like this. And the difference is that the first one, the epi, all the 3 here combine in one. The second one, we have a 3 perturbation variable, and then the epigraph separate in the 3. And the last one, F, and separate with the second thing. So it's 3 ways. So now if you do like this, and then you will have, you apply it to the general Fu like this. You apply the theorem 1 and 2 before, and then you get at least 3 kinds of Farkas lemma for this case. For the first, if you apply the Fu, the perturbation in the form Fu, you have this form. So this is a Farkas lemma. But you see, here is 3 things in combined, 3 functions combined together with star here. And then we have this form of Farkas lemma. This form of Farkas lemma, and the condition for this is this one, and we also have here the duality. And the reality here is, of course, you can, if we consider the problem like the problem, we have a footnote here, and then that is a duality result for this. And if you use, and for the convex means what? You have, if the sum here is convex, if you have a k here, of course the convex and lower semi-continuous, and then by the Morrow-Rockefeller, you have k equal k double star. But here we don't need the whole thing. We need only for HU of x. We have this one, and then we have here, in this case, the set B is which are close regarding this one. Then we also have this thing, this 3 can. So in this is whenever you have the set A is A now become B, and we have the similar things, A becomes C, and the A become D. Is that okay? But in this case, actually the convex. So with the convex, and then I have this one, and if you use the Fu in 8, we also get similar robust Farkas lemma with the set B and C, C instead of B, and then if you that's okay. Instead of you will, because here we are in the convex case, and then we can apply to the DC problem. Is that okay? And if you use the perturb formula 9, and then you have the same thing, and the set D instead of B there. And now the yes, we have about 15 minutes more. So now I just want to say that, okay, all the result in this section is on the first Farkas lemma for this special case. And then now we apply to very special like this one, and then we get special Farkas lemma for this. For example, if you apply to this situation, and then I get Farkas lemma here. H, U, X belong to the U belong to U, C belong to C, X belong to C, imply this one, then equivalent to this. Then we have this one is one kind of Farkas lemma. Is that okay? And the condition is this. This. Of course, in this case, the set B, we are in the situation of the set B, but the set B now become like this. And the set C become like this, the set D become like this, because BCD with the three kinds of perturbation. Is that okay? 7, 8, and 9. But we apply to this situation, the situation of this problem. Is that okay? Then it becomes some set B prime, C prime, D prime. And the general Farkas lemma in the first part give us, so it means that this condition, if and only if this condition. And this is Farkas lemma. So that means that you have here the first part I is a Farkas lemma, this form, all the 3 star here, that is this one. And the second one is the star is separate into 3 parts. This one, this, rather than this one. And if and only if this condition satisfy. And this one, the last one here is just divided into 2 parts. One this, and this is combined to this. So that means that all the combination of the conjugate of the function give us. So we have this one. But and of course, when you have some situation like a V equal to the whole space, or V equal to only the vector 0, and we can have something like this. For example, when V equals 0, and then the function h now become a constant, and then we have the Farkas lemma for this. This f is convex, and it's only Farkas for convex. So we have this thing. So now the second thing, robust DC of this way. No, it's just a moment. What is it? Yeah. In this case, we don't assume we are general robust conical constraint problem. That means f and h and or everything, the function f is not convex. The very general. And now, if you consider a f is convex, h is convex, then we have the DC. And in that case, we have something different here. So, the robust DC problem means here is convex, f is convex, h is convex, h of u is convex, c is convex. So everything is convex. And then in this case, we have some Farkas lemma like this for the convex. And in the convex case, you see that it's not close regarding in the form close regarding, but it is just we saw close regarding this one. This. So you see here is different. The condition here is different with the what you had before. What you had before is epi of this intersection with this. But now you just in this case, this later case, you just focus on this set. We don't care about the epi because in that case, epi of p star is equal to the closure of that. And so you need the closure, and then you have this one. So it is like here. So this is 3 kinds of Farkas lemma corresponding to the 3 way of perturb the function f. So, and with all of this thing is about the convex case DC, but the infinite, there's many the different form up here. And we also have a Farkas lemma, and now is to the convex. You see 5-3 is to the convex. That means you have the only one function f here, and in special case you also have a lot of form of Farkas lemma. And here is to the this is for the linear general system. We have this one, and the set A now become very simple like this. And then the Farkas lemma, we also have something here, this. And we consider here the set the linear but semi-infinite. So you have here the inequality, linear inequality for all t like this. And then the Farkas lemma also have this form. And now the last thing is I just want to show you very quickly that we consider here we consider the case of convex. So that means here is a DC problem under the uncertain convex constraint. And this I think that in the literature talking about the optimality condition or the duality for this kind of problem I have not yet seen anywhere. But if we apply our result, then we can have the strong function duality for this. It is like this. So that means that if the value of the primal problem here is finite, and if the set, the regularity condition is satisfied, that means the set C prime, which are close regarding to this, then the strong function duality hold for this. It means that it is, we say yes, that it is in the DC, and then we have this. So that means strong duality hold. And if you come to the convex, and then the duality also hold, but the C prime is weak close regarding this set, special set, and the dual, the function dual like this. But for the convex problem, the function dual, we also have some Lagrange duality. If we change, we write down the Lagrange duality like this, and then you also have the Lagrange duality like this. But because we use a V, we use a set V, and this satisfies for all x star belong to V. Then we call, like the primal problem is x, but it's perturbed by x star. It's a linear perturbation. So the duality hold for any linear perturbation function x star from the set V for any this, and so we call this stable. And the result is normal. That is, so if the set is with B star, B prime is now it become like this. If it is with star close convex and regarding to this, and if and only if the Lagrange, the very stable Lagrange duality here is whole. And of course here something special kind of convex, special kinds of convex problem, but the infinite constraints. And then we also, in this case, the Lagrange dual problem is of this form, and then we also have some strong duality result for this. Of course, we in the paper we have some more dual problem for the linear case, linear problem, semi-infinite or something like this, robust linear, robust semi-infinite, something. But that's just enough. I think it's too long now. So these are the some of the reference, and the paper is also after working with some special class, and this is something like the last generation for this. And then we have something that unifies all everything that we made before. So thanks very much for watching, for listening.